Welcome to our first presentation of Views and Sounds from the Limnology Center Archives. This is put together by myself, John Magnuson, Victoria Rose Finley, student archivist, Marvin Tan, who knows how to work with these things, and Martin Magnuson Berg, my grandson. Edward A. Burge and Chauncey Jaudet founded the field of limnology in North America, and they did it here at the University of Wisconsin. Burge was an active faculty member in zoology, became dean of L&S, and eventually president of the university. He was a busy man in his later years, still loved limnology. He brought Chauncey Jaudet to the university, and Chauncey did much of the teaching. He taught the first limnology course. He mentored the graduate students. He became the first president of ASLO, and he conducted the field studies that were done at Trout Lake in the later years pretty much on his own. They were a productive pair, and they produced almost 1,500 pages of scientific papers together, many of them published in the Wisconsin Journal of Letters and Sciences. Clifford Mortimer in '56 quoted what he thought they would be known for. I'll let you read that on your own. If you have the time, I suggest you go back and look at some of those papers. Many of the things we take for granted are there, and they weren't there before Burge and Jaudet. Burge and Jaudet had many collaborators across the campus. One of the best known and interesting people was Hattie Bell Merrill. She was an early woman who stood out. She ran his limnology zooplankton laboratory in Burge Hall. She made trips to South America to collect zooplankton. Many of those collections were deposited at Indiana University and worked on for many years. She died fairly young. I recommend that you read The Anadrous Journey, a story of her life written by her great niece. One of the cabins at Trout Lake also is named after Hattie Bell. As I mentioned, Burge and Jaudet had many colleagues, many of them named here. Stillman Wright was one of graduate students of the Jaudet, and for South America did the same thing that Burge and Jaudet did for North America. There are many other names here that you may recommend. Notice Noah Nolan, for example. The earliest footage we have for this archive survey was E.A. Burge himself, 1929 in Burge Hall. He was very, very interested in Daphnia and zooplankton, and his initial interest was in their taxonomy and systematics. Later, he became interested in why they vertically migrated, and that led him to an interest in limnology itself and the physics and the chemistry of the lakes. Art Hasler was the second leader of limnology at the University of Wisconsin in Madison. He was one of Jaudet's students. He taught limnology and fish ecology in all his years, but he studied also animal behavior, orientation of fishes, and actually really added fish into the field of limnology. Fish were very much a part of the system. He and his students worked on them in a variety of ways. We have a lot of footage. We have many clips of Art Hasler and his work and his students, which I'm anxious to show you. Some of his major characteristics were he was really an environmentalist. He'd been influenced by Leopold. He, along with Tienemann in Germany, were leaders in the early work in experimental limnology, whole lake manipulation. As I said, he added fish. He worked on Lake Mendota and tried to deal with its problems. He was very much an internationalist. He had many, many graduate students and interacted with faculty across the entire campus. He was an institution builder. He built our field station here on Mendota and also at Trout Lake. The people listed here include many of his graduate students, many of his faculty colleagues across the campus. Perhaps the best known is his student Gene Likens, who's on this list. Bill Schmitz, a graduate student of art, who taught at Wausau and managed the Trout Lake Station, including the building of the new lab. Perhaps the least known student is George Gallup, who received a master's from me and a PhD from art, and ended up managing the Trout Lake Station and staying there over the year. He died young, and we miss him. This is the first views we have of research by Art Hasler and his students in 1955. Notice the ONR impulse. It was provided by the Office of Naval Research. NSF had not come very far in terms of granting grants by this time. It was a fairly young organization, and Arthur was good at getting resources from ONR. Notice the Alumacraft. I think we're still using that today. They're out vertical gill netting for yellow perch. John Tibbles was studying the vertical distribution of the perch in Lake Mendota. Lake Mendota perch were very abundant. Notice the vertical gill nets. We started using these also again at the beginning of the LTR program in the early 80s. Not the same ones, but the same design. Note-taking was with pencil on open pieces of paper. Perch were plentiful. Occasionally we'd catch a northern pike and would safely return them to the lake. They had another boat also rigged up for doing vertical gill netting. This is Art Hasler on board, and I believe John Tibbles and someone else, but it's essentially a pontoon barge. And they use both the pontoon barge and the ONR impulse to measure these fish. Notice these yellow perch are really near the bottom. That was a lead line that had come up. They also did this winter gill netting to study the distribution, vertical distribution during the wintertime. They would put planks across the ice ridges to be safer. This Jeep was also provided by the Office of Naval Research. Notice that the sign for the activities out here was called the Lake Lab. Getting through the ice was not too far different from what we do today. Also, we didn't cut off anybody's toes. What they're doing is making a trench or a hole through the ice. It's elongate, and they will set the vertical gill net down through that, as you see here. They would set a set of these and roll them up and down the same as they did with in the summertime. Recording again was pretty crude and rough. Perch fishing was quite popular. There were a lot of perch in the lake, and there were a lot of fishermen out there, and they were catching perch. They were very interested in what the lab was doing. Yep, there comes one. A number of Arthur's early students studied yellow perch. John Bardock was the first. Don McNaught wrote a nice story about the fishes on Mendota, and John Tibbles studied this vertical distribution of the perch. They were very abundant. Tibbles was trying to explain the vertical distribution. So they not only sampled the perch, but they had an ice drill where they could put down sampling equipment for chemistry and for benthos and a variety of things. Their drill was a bit more cumbersome than the one we use today. Here's the Ekman dredge they used, not very different from the ones we use today, used for sampling the benthic insects and helping explain why the perch were where they are. The ones today are made out of stainless steel. The Office of Naval Research also provided Arthur and his students an acoustic device, a sonar for measuring the vertical distribution of the fishes. Notice the generator alongside, and this is an early model of a sonar for looking at vertical distribution. This next set of sequences just before the modern limnology lab was built and shows a student out sampling water in 1962. He's going out from the old Lake Lab pier. This pier extends out from the old lab building at the foot of State Street. Notice how they get into the water. Notice the whaler looks like some that we have today. The student is taking dissolved oxygen using a Kemmerer water sampler. Kemmerer was also associated with the University of Wisconsin-Madison. And in he comes. The hydrobiology lab was built on Lake Mendota shoreline, started construction in 1962 and was finished in 63 and dedicated. The building was designed by William Kaiser, an architect, and we presently have a visiting scholar program funded by him and his family. Arthur Hasler had obtained the funds for the laboratory from the National Science Foundation, and it aggregated both his research and his teaching efforts here. Prior to that, his office had been in Burge, and his laboratory was the little brick building at the end of Park Street. If you look in the parking lot, these automobiles were designed in a space age with the U.S. space program that followed the Sputnik landings. The building was dedicated in April of 1963, and in 2005, we renamed the building the Hasler Laboratory of Limnology. Note there's already an antenna on top of the roof. An important feature of the lab was that it provided direct access to the lake by boats that were stored in the slip. Only a couple years after the lab was built, Art and his graduate students were tracking white bass to determine whether they had the sun compass orientation abilities in order to find the shoreline in which they had their spawning sites. They caught the white bass near the shoreline and then would transport them to the center of the lake where they released them. And much of the footage in this section was taken by Art Hasler's older son, Fritz Hasler, who was a good artist and photographer. They'd process the fish. Whoops! He learned. Time to remind you that Art always included fish as part of his studies of limnology, or what was often called at that time hydrobiology. Initially, they were tracked by attaching a floating cork to them and then following them at the surface. Next, they designed an acoustic tag or transmitter that they could use to follow the fish underwater. It was designed by Jerry Chipman and Fran Henderson. I have pictures of Jerry Chipman and Fran Henderson coming out of the limnology lab door. Both were key members of the staff working with Art.
Hydrobiology, a fish story with Dr. Arthur D. Hasler, Chairman of the Zoology Department, University of Wisconsin. And here to introduce Dr. Hasler is your program host, Donald Andresen.
Right now I'd like to talk with Dr. A.D. Hasler. Dr. Hasler is the chief in charge of the Lake Laboratory and all of the experimentation that goes with it. Dr. Hasler, would you tell us exactly what the function of the Lake Lab here at the university is?
Our Lake Laboratory is principally for the study of problems on Lake Mendota. In fact, any problems that have to do with aquatic animals.
Most important experiments that you are now engaged in and have been for a number of years, I understand, is trying to find out how the fish finds his way home. The most striking example that comes to my mind, and probably most people's, is the salmon and how it returns from hundreds or perhaps thousands of miles away to return to his home stream to lay his eggs and die.
Now, the evidence for this rather precise of the homing is very striking, I think. One Canadian investigator marked some 400,000 individuals as they were migrating to sea. And when this class of fish was to come back from sea 4 years later, they put traps on all of these streams and found something like 11,000 of them. but not a single one of these 11,000 had moved into anything but the home stream.
In other words, all the fish that were retrieved were ones that originally came from that stream.
Exactly.
No strays.
Well, in this case, there were no strays. There are some other cases in which there have been a small number of strays. But this is as it should be. Things are never 100% in biology.
Well, I guess that takes us to the question, how do they get back? I know, as we've discussed before the program, that your laboratory has pioneered research in certain areas. I never knew, for instance, that a fish has a nose. Maybe you could tell us about this.
Well, this is leading in, of course, into our research work in which we attempted to explain the manner in which a fish returns unerringly to its home stream. And one hypothesis that we proposed was that the fish returned to its home stream because of some characteristic odor. We had to establish in this hypothesis was to be able to ask the fish a question of, can you tell the difference between stream A and stream B? Without this fact, you wouldn't be able to proceed further with this hypothesis. And so we went on with a series of tests in which we designed apparatus in order to ask this question. These fish are dumb animals. They can't talk, so we must ask a question in a way that their behavior will give us the answer.
And this you did in the laboratory.
That's right. Here is an example of our apparatus in which the animals are placed, the fish are placed in a tank of this type. Odors can be introduced through those containers here and entered at the bottom so that the fish can smell the odor as it's introduced. The fish can be either shocked or punished here, so that we run the fish through a series of tests in which punishment and reward are the ways in which we get at the answer.
Well, go ahead. I was just going to say, shall we look at it?
Perhaps we can show you a film which illustrates in a typical series of tests. We find on the right side of the tank the scoring zone, and during a minute of observation period, we chart or score the fish as they move across this barrier at the right end. You notice these fish are rather lethargic. They're moving rather leisurely about this container, and I want you to note when the next sequence comes on how dramatically this behavior changes. And if we had time to show this next sequence, you'd, I'm sure, impressed with the fact that they would avoid this area when they receive the odor on which they expect punishment. And so this test has proved that fish are capable of sensing the odor of two different streams. And we've answered the first question, a long series of questions which we must ask to arrive at some substantiating evidence of this hypothesis.
You then went in the field, I understand.
Well, we felt that we had to go in the field. There were a number of other tests that we won't have time to tell to bolster this program, but let's give you an example. We put traps on streams at this particular place and at this place to capture fish that had chosen this home stream and this home stream and displaced them to this point and asked the question, can you find your way back to the original site? Let's just show now in the next slides. Displaced down here, the normal ones went back precisely. For instance, if these are A and these are B, transfer down here to B, A and B, they went back without any great number of errors. But when you stuff the noses, as you can see on this next slide of the fish, stuff the noses with cotton, deprive the fish of the sense of smell, and put an equal number of those down at this particular point, we found that these made a number of errors, and so the A's went to B and the B's went to A, randomly showing that when the sense of smell was disturbed in adult salmon, that they no longer were able to make this choice at this junction. But it seemed to fit into the general hypothesis that the nose was an important organ for sensing the environment and helping the animal to make the choices in the upstream migration toward the home stream. We have other projects in mind that we would like to have our colleagues who are closer to this problem try in the West Coast, but I think that we'll have to wait some time before we get the more complete answer on those additional tests that we feel have to be done to prove this hypothesis.
Meanwhile, you're continuing here in Wisconsin on, I believe it's the white bass.
Well, that's right, Mr. Randall, of how they get home from the open water. And we have, very fortunately, in Lake Mendota, a white bass. You see it here, Grayson. We felt that one area in which we could make a contribution to this general problem of how animals get home would be to tackle the problem on these two sites in the spring, early summer of the year, on the bluffs of Maple Bluff and on the bluffs of Governor's Island. One of my colleagues, Mr. Horrell, has worked with me for a number of years on this, and he has displaced, with the help of other men in our laboratory, literally thousands of fish, marked them, and put them into the middle of the lake, and found that year after year these fish come faithfully back to these two sites. And do not confuse them. That is, the fish from Maple Bluff never go to Governor's Island, at least by never. In a small percentage of the cases they do, but the majority know they're off. And we have found by this test that these animals do migrate in a large percentage of cases toward the north shore of Lake Mendota. And we have termed this observation the north tendency. And several years of data show that, at least at this time, we feel that this north tendency is real. It may be that future work may prove us wrong, but at least with the data we have at hand, these fish seem to migrate toward the north shore. This might not be the case of the fish that was spawning on the south shore.
Well, in the case of a lake, it's not only odor then that would send them to the north shore.
Well, that is a very good question, because it so turned out with these animals that when they did migrate only to the north, when they did migrate faith to the north when released from the center, and quite directly so, they did better on sunny days than they did on dark days. On cloudy days they would box the compass and seem to be fairly confused and oriented, as we call it. This led us to the assumption then that possibly the sun was the cue that the fish was receiving, which with its internal reactions and mechanisms set it off in the direction, in the homeward direction.
And this takes us back to our tank, which I started off with earlier this evening. This is a part of the sun orientation tank, part of the research then.
That's right. We felt that this mechanism could be investigated by a laboratory procedure. That is, the ability of the animal to use a cue, a celestial cue for orientation, could be approached by a laboratory experiment. This is a tank we call our sun orientation maze. And you'll notice that it has a trap in the center in which the fish can be placed. We can expose the fish to an artificial sun, which is our one we have in the laboratory is a much more realistic sun than that one. So, well, if you'd like to see it, let's call Nancy over here and see if she'll run through us a mock experiment, a mock test with the fish. We'll put a fish into this central compartment here, and
first of all, Nancy, would you show us how this compartment raises and lowers?
This is the releasing mechanism for doing that, Mr. Andresen. And in the training process, 15 of those holes will be closed, and he can only find a place to get away from the experimenter and irritation by going into that one. That's the training process. We've got to remove all extraneous stimuli.
There he goes. Will he make it?
Well, he did. He made it. Well, this is, let's go back to our test. Thanks, Nancy.
All right.
Go back to our charts here to give you some idea of what kind of data we get from a machine like this. And if we can have this first slide, Andresen, we'll show you how we score this. You see the apparatus that we just saw with the containers into which the animal will show you the results of a trained fish which has been trained with the sun as his only cue. The sun now is here on this diagram. He was trained to go to the north container. In this series of tests, you can see that he spread some, made one very bad mistake here, but in general seemed to have learned the lesson quite well, that in the morning, in the forenoon, when the sun was in the east, he was well oriented as to the northerly direction. Now, the next slide, because when the sun now is in the west in the afternoon, these scores again are in the north. Here the sun is in a completely opposite part of the sky, and yet the fish has performed quite quite accurately, showing that this mechanism within him, which uses the sun, which is timed by the sun, gives him this direction. It's something like a Boy Scout, if you want to put it in that kind of an example, with a clock and a matchstick, being able to find his direction.
This research that is done, are papers published on it so that it is known throughout the professional societies, the work that is being done here?
When we feel confident that we have a set of results that can withstand our own criticisms and those of our colleagues, these are written up and published in the national scientific magazines, and magazines like Science, like Limnology and Oceanography, and journals that have to do with marine and aquatic science.
I understand that you got a letter from a gentleman in Australia, which I guess points up the fact that actually this information does get very far abroad. Would you tell us about that? I think it's quite interesting that a subject such as this will draw reaction from all over the world.
Well, this gentleman of whom you speak, a scientist from Australia, has heard about our work, has no doubt read the publications that we have published in the last 8 years, and in discussing this with the officials of his organization, have decided to set up a fish behavior laboratory and to investigate rather intensively the spawning migrations of the Australian fishes. And he has asked to come here for 6 months and learn our methods and try to develop a technique that he can use to approach some of the problems down in Australia. And we'll return there, no doubt, and work on some of the problems of their fishes in this area.
You have a chap here now from Germany working with you right now, don't you?
That's right. We've had a number of foreign scientists in our laboratory working on this problem as well as other aspects of hydrobiology.
Thank you very much, Dr. Hassler. I'm sure that this has been most interesting to our guests. I know it has been to me.
Glad to have been with you, sir. Goodbye.
Hydrobiology, a fish story, featured Dr. A.D. Hassler, professor of zoology at the University of Wisconsin. Hydrobiology was produced by Donald N. Andresen and Earl Grove. Directed by Ralph Rosen. Produced in cooperation with WHA-TV.
Welcome to the Trout Lake Station, winter 1970. I was studying the behavior ecology of fishes in a winter kill lake because I was interested in the vertical distribution in response to temperature and oxygen gradients, and I'd gotten the ideas from working in the Central Pacific. We did this work in Mystery Lake, a shallow lake in the Five Lakes area in which the oxygen tended to disappear over the wintertime, and the fish often would winter kill or die from the loss of oxygen. Some of the tools we use are pretty familiar to you. We always seem to have trouble getting them to start, but they did. We established a set of stations out in the center of the lake, and in these stations we provided ways to sample the water from the top to the bottom, and we also provided a way to observe the fishes using a periscope that we ran down from a tent. The temperature meter was one that had been designed by Whitney. Later on, he was the president of a company called the Whitney Monadero Instrument Company. Here's the sampler that sampled the water at different depths using a siphon principle. There's a Tygon tube that goes from each of those little knobs on the side up into the top of the container. We put an oxygen water bottle sampler, push the Tygon tubing into it below the top of the water level, and the water starts to fill the jar from the depth that that Tygon tubing was attached to. We put in the reagents. We used a Winkler method. We did not use an oxygen meter. We add a number of reagents and mix them and shake them. Later we added a third reagent, and mixed it again, and the darker the color, the more the oxygen there was. And so here you see 4 samples from 4 different depths. The one on the top, that one didn't have much oxygen, that would be near the bottom. The one at the top had more oxygen, that would have been just under the ice. This is Jim Herbert. Meet him. Hi Jim. He is a commercial fisherman now in Alaska. I can tell you more about him later. Anyway, there's our sampler. You can see all the knobs which represent where the other end of the Tygon tubing was placed. This is the area we cleared of snow. In the center of this, under the ice, there was a net containing fishes, and we pushed this wagon or this tent over that hole and lowered a periscope into a plastic air-filled tube and could observe where the fishes were in respect to the oxygen gradients. We also had trouble starting our snowmobiles. It wasn't a Jeep this time like Art had. You probably don't recognize the design. If you watch closely, you see one of my good colleagues make a snowball, and as soon as he goes by this bushes, he throws it at me and tries to hit me. I was the photographer. Anyway, another day's work. Samples to be titrated in the lab to determine dissolved oxygen.
My name is John Magnuson. I'm a professor of zoology at the University of Wisconsin at Madison and director of the Center for Limnology. Limnology is the study of inland waters, sort of a freshwater version of oceanography. What I'm going to talk to you about today is unveiling invisible present. And this clock sitting in the dark is meant to symbolize how the world about us really seems if we don't take rather specific approaches to putting the present into a larger spatial scale and into a larger temporal scale. Ecological research, which I'll be talking about, has difficulties sometimes by being obsessed almost with what you see in front of your feet at any particular point in time. And so what I'm going to be talking about is some new approaches that we've been using to try to unveil, if you like, the invisible present. There was a book called The Fifth Discipline written by P.M. Senge, and in it he has some really choice quotes. A fundamental characteristics of complex human systems is that cause and effect are not close in time and space. This book is designed for business managers to how to make an organization become a learning organization and respond to the system around it as it really is. And so one of the problems here, it's not that things are not closely related in time and space, it's that most people, most of the time, assume that cause and effect are closely related in time and space. And it's that issue that I'll deal with here. And that also that there are delays between actions and consequences, and they're everywhere in human systems. But the delays are often unappreciated, and they lead to mistakes if you're managing a business. Well, Senge, in his book, argued that we need to have a shift of mind. We need to see interrelationships rather than linear cause and effect change. We need to see processes of change rather than snapshots. Those of us who are in ecology really enjoyed this book, which was a book on how to run a business, because if we had taken out the word complex human systems and had just put ecosystems, or if we had put complex ecological systems, including humans for that matter, it seemed to ring a bell with us. With here in Wisconsin is we're the North Temperate Lakes site, and we have a group of lakes in northern Wisconsin, in Vilas County, not too far north of Minocqua-Woodruff, and we have the group of lakes that sit here in Madison, the Madison Lakes. And it's those lakes that I'll be talking about today. And first, let's give an example of what I mean by the invisible present. The Europeans that first migrated to the Madison area started recording 2 phenological events, temporal events, sort of like the blooming of roses and the first robin, but they recorded the date that Lake Mendota froze every year and the lake that Mendota thawed every year. And they've been doing this since the middle of the last century. And I'd like to use that data record to show what happens when you look at the present, the invisible present, and then start opening up the time series and begin to see what happens. First of all, here's my version of the invisible present, and we'll show 1983. The rest of the record is blanked out. And the duration of ice cover in 1983 was about 50 days, only a couple of months. I'd argue that that's not too interesting, and you might forget it by tomorrow. What I'd like to do is now show you what happens. First, open this time series up to 10 years. Already, 1983 makes a little more sense. You now know that 1983 is an unusual year. You also, even though it takes tremendous amount of calories and heat exchange to freeze and thaw Lake Mendota, you see that in just this 10-year series, there are some years when the ice is on the lake for over 110 days and others only 50 days. In other words, almost a doubling in some years. So we see that this is a highly variable thing, and now we see that 1983 is an unusual year. Well, let's open it up to 50 years. Well, now 1983 is no longer an unusual year. What we've done here is we've put black dots on every one of the years, which is what we call an El Nino year. Now, El Nino is a change in the circulation of major circulation centers and pressure zones around the globe. And it got the name El Nino because of oceanographic changes that occurred off Peru at around Christmas time, and El Nino was the Christ child. Well, it turns out that those changes are interconnected by teleconnections around the whole globe, and so these circulation patterns change rather dramatically. In an El Nino year, those are the years you hear about all the flooding in California. And there are events around the world associated with this event, not caused by El Nino per se, but caused by this shifting of these global air masses. What you can see here now is 1983 is even more in context. It is not an unusual year. It is, in fact, a year of low ice cover associated with a major shift in the climatic circulation around the Earth that occurs at a short interval. Let's open it up to the full length of record. This goes back to about 1850. Now you can put 1983 into even a greater context and help remove it further from the invisible present. First of all, it is an unusual year. It is the shortest duration of ice cover that Lake Mendota ever had, and has had since, by the way. This is an El Nino year, and I was waiting for this year, 1995, to surpass this, but it didn't, but it almost did. The other thing you can begin to see now is another pattern. You can see global change or climate change. If you look at the record prior to about 1880, you'll notice that while there's a lot of variability, that the duration of ice cover was about 120 days. If you take from around 1980 to the present, you see that it's closer to 108 days or 110 days. Now that shift, that sudden shift that occurred in the last part of the last century is known as, among climatologists, as the end of what was called the Little Ice Age. The Little Ice Age was a period of colder weather in the northern hemisphere that lasted for about 300 years. And here, this record on Lake Mendota picks up that change well before we had weather stations tracking that kind of thing. Well, in fact, here's an ice rampart across Lake Mendota that I kind of like because it almost characterizes the pattern of year-to-year variability that you see not only in ice cover, but in many of the variables that are around us in this world. Another reason that we get lost in this invisible present is because there are a lot of time lags that occur in systems where there's something that happens and the result of that doesn't occur immediately, but in fact that occurs a number of years later, that in fact there are time lags greater than a year in duration. And I don't know how you are, but you know, this summer is rather hot right now, and it's hard for me to remember whether it's as hot as it was last summer. The first one I'd like to talk about is just the time lag that would occur in any population of organisms, such as these trees in the Cascade Mountains and the Oregon Pacific. If you look at any population, and if that population reproduces in any year, in this case year 0, you start out with a large number of young, a large number of individuals, but they're all very tiny. The top graph shows that we have a continuing decline in the numbers. This is true whether we have a large year class of perch in Lake Mendota, of chubs in Lake Michigan. The second middle graph shows what happens to their body sizes, and they grow larger each year and eventually reach some maximum size. The bottom graph shows what the biomass of that cohort looks like. If you have a lot of organisms at time 0 but they're tiny, you don't have very much mass of those trees or those fish. If you wait until the end of a period, the organisms are big, but there's only a few alive, and again, you don't have much mass. There's an intermediate point, and this is sort of geared for something like a perch population. In this case, around 2 or 3 years, the biomass of that perch cohort, that year class of cohorts, is maximum. So if there's an event, for example, that causes a strong year class of perch in Lake Mendota, and those perch eventually affect the populations around them by feeding on them, or they affect populations around them by being prey, the maximum effect has a time lag here of 2 to 3 years, just because growth and mortality is a slow process. So that's just a time lag that occurs because some biological processes are slow. The next ones I'm going to tell you about is a Wisconsin case. This is a small lake in northern Wisconsin. It's called Sparkling Lake. And it's right on Highway 51. The lake in the background is Trout Lake. It's a little bit north of Minocqua. This particular lake has had a time lag in a cause and effect, which is the local extinction and extirpation, if you like, of a native species. We use the word extinction for global, and we use the word extirpation if the animal disappears from a particular lake. Well, the animal is called the cisco, or the lake herring. It's a cold water relic that was left in the area after the glaciers receded. It lives in the midwater, and it eats plankton. This particular species arrived in the lake. It's called the rainbow smelt. Originally, its range was in the Atlantic. Somebody moved it into a small lake in Michigan. They ran downstream, got into the Great Lakes. They ended up in Lake Superior. And somebody must have taken some from Lake Superior down to this lake, and it colonized. Let's see what happened to the population. The blue is the cisco, and that's the native fish, and the yellow is the exotic smelt. The first year that we sampled, 1981, we did not catch any smelt, but we caught quite a few cisco. As the time went on, there were several successful reproductions by the invading smelt, and slowly the cisco became less and less abundant, and we haven't caught any since 1989, and the species has gone extinct. Now, there was an invasion, that was the event, and there was a time lag of almost 10 years before the native species went extinct. And in fact, the mechanism of this extinction was that the cisco was preyed upon by the smelt only at a certain point in their life history. The cisco, as young, are in shallow water early in the spring, and as the surface water warms up, they swim to deeper water. And as they swim to deeper water, they swim through a gauntlet of these smelt that are sitting at an intermediate level. And so they're all eaten. And it wasn't that the smelt didn't spawn summer of life. And if you sampled the cisco population in 86 and 87, what you found is every year you sampled, the population was composed of animals that were 1 year older, and there was never any reproduction. And then when the last reproductive animal died, they went extinct. A time lag caused between cause and effect that often confuses your understanding of it. Now, these are not just true for observations of the natural system. Those of you who might be thinking of doing a master's experiment and want to get it done in 2 years, or a PhD and want to get it done in 5, I'd like to show you what can happen to the invisible present when you do experiments in long-term ecological research. So what are we going to do here? We're going to do an experiment that lasts more than 1 year, okay? Now, where this experiment that occurred is a person by the name of Tillman. He's a professor at the University of Minnesota, and this is a natural area north of Minneapolis and St. Paul called Cedar Creek. And what he did is he had a series of plots that you can see, and he would treat those plots in different ways, and the treatment I'm going to show you is an addition of nitrogen. And then he would see what happened to the community of plants over that time. Well, the first year is when you see year 1, that's when the nitrogen was added, and then you can see what happened year 2, 3, 4, and so forth. Each of the panels, the top one is perennial ragweed, the middle panel is the populations of bluegrass in these little grids, and the last one is blackberries. The black spots are the treated sites, and the hollow sites were the ones that no nitrogen was added. Let's say you only studied it for a year. then what you would do is you'd look at this and you'd say, well, you put on nitrogen and what you get is a tremendous growth of perennial ragweed. Not much happened to bluegrass, and nothing at all happened to blackberries. If, in fact, you were a little slow and you didn't quite get your thesis written and you worked the next summer, you would have said, uh-oh, I was wrong. In fact, what this treatment does is it causes a growth in bluegrass and not perennial ragweed. And in fact, if you're really slow and don't finish your thesis for 5 or so years, what you would conclude is adding nitrogen caused this community to shift to blackberries. Now, what's happened here is that there's time lags between causes and effects. And what this person was studying was a transient. Hay had set an action in motion, and the motion did not, the activities, the processes did not play out in a single year, but played out over a series of years. So these time lags also get involved in experimental things in natural systems.
I guess that's it. Thank you very much.
Thank you very much. You've been a very energetic and patient audience.
It looks bad, it smells bad, and it can be just plain unhealthy. That's what happens to a lake overrun by algae. But researchers think they found a natural way to cure a sick lake. CNN science editor Charles Crawford has the story.
From a distance, Lake Mendota sparkles in the sunlight, a picturesque 25-square-mile body of water. Wisconsin's capital city, Madison, hugs its shoreline. Over the years, it has been one of the state's most popular recreation sites. But today, Mendota, along with thousands of other lakes throughout the nation, is in trouble. It is choking to death in algae. The tiny plants turn the water a sickly green. When the organism dies, it creates a foul odor and can produce a toxin deadly to small animals. It also reduces the oxygen level and the lake's ability to support large game fish, such as northern pike and walleye. The situation has prompted State and University of Wisconsin researchers to try a novel approach to restore balance in the 10,000-acre lake. They're manipulating the food chain so that natural predators will eliminate excess algae. Under a microscope, the algae show up as dark blobs. And these wiggly creatures are a zooplankton called Daphnia. The microscopic animals feed on algae. The goal is to increase the number of zooplankton, which in turn will consume more algae. Unfortunately, zooplankton itself is a tasty meal for small fish in the lake. So, to ensure survival of the algae-eating Daphnia, the Mendota Project is stocking the lake with over 100 million juvenile northern pike and walleye that will grow into bigger fish.
These large fish, we theorize, will eat the small fish, keep the small fish densities very low. This will allow small grazers, zooplankton, to proliferate and consume the algae.
2,000 grams?
This lake is an example of a novel management practice on a very large experimental scale. And if we succeed here, we will have demonstrated a technique that could be used very widely to clean up lakes throughout the country or throughout the world.
It will be several years before researchers know if the stocked fish can clean up the murky waters of Lake Mendota. But if the experiment works, the lake not only will be cleaner, it may become one of the best fishing spots for northern pike and walleye for miles around. Charles Crawford is CNN, Madison, Wisconsin.
Science and Technology Today is brought to you by the people at AT&T. AT&T, the right choice.
Freshwater ecosystems, hydrology, and water resources.
Move forward, aquatic systems and water supplies.
Well, first I'll answer the questions that were put to us. From my perspective, what are the controversies? I think the controversies on freshwater ecology is whether we should include it at all in the assessment. I was originally on a group called Oceans and Large Lakes, and freshwater tends to drop between the oceanographers and the terrestrial. And oceanographers sort of view lakes as not interesting unless they tell them something about the way the ocean behaves. So oceanographers don't fight for you. The terrestrial people tend to think of the world as being divided into biomes, but in fact our lakes are distributed across the world, and our streams and wetlands, not in respect to biomes. They have a metric of their own by which they're distributed, and some of the lakes in one part of the world are very similar to lakes in another part in another biome. Another controversy we had was supply versus quality in terms of water. and the water supply chapter just dealt with supply rather than with water quality. This group right here could decide that the outcome they were interested in is proving that there was climate change, warming, that was dangerous.
Case making. Yeah.
I mean, you could take a debate format and aggregate information to make your case versus trying to improve the state of science and understand how the system works, and if it didn't produce the results you had expected, say, well, that's interesting, and just keep going. So it could be any one of us. What I'm going to talk about is freshwater ecosystems, hydrology, and water resources. And this interest area was, how many alternatives are there?
It's the repeat of the wrong.
This interest area was scattered throughout many different chapters in the assessment. The cryosphere is all about water. Lakes and streams were sort of not included. Wetlands were in a subsection, and there were marine and coastal wetlands. Oceans is water, hydrology, and water resources. So the people that were involved, as the terrestrial ones as well, the wet people were scattered amongst the different subjects. The bottom line, in terms of the major results of the water things that I was associated with and the water resource section, is the water supply per person is declining, water for irrigation supplies are declining, wetland areas are declining, cryosphere ice, this stuff's declining, and these things are increasing. And most of these results, no matter which of the two chapters they were in, were given with what I would say were sort of high confidence. In these two chapters, there were really serious problems that were caught about midway through the process by the peer review process and by the secretariat, or whatever you want to call it. And there were strong personalities, but I think the issues won. I mean, I thought it, maybe it was painful, but in fact I thought it won. The system was responsible, and I thought remarkably flexible. Gone.
The cusp maybe of switching from a rain to an ice storm. And actually this is quite an opportunity, this seminar series, because John and I are expecting to have to start going out on the road now and giving more presentations. One of the things that we've really seen in this past decade, and it's a trend that we're expecting to continue, is the increase in the extreme precipitation events. And that causes, of course, runoff. Well, last year was a banner year for flooding. And here are some shots from, this is the dam blowout at Lake Delton. Here's a shot from previous years up in city of Anago, but Baraboo was completely flooded. I mean, the damage to our communities is tremendous with these kinds of major big storms. This is kind of a depressing talk. I mean, we got a lot of problems in the future. How are we going to deal with them? But we can change. We can adapt. And I think Dan will show you that if we do some mitigation as opposed to business as usual, the future won't be as bad as if we do make an effort to change. And so that's the ending message that I would like to leave, that we need to make changes now, but that we can and we will make a difference. Thank you.
One of the things the ice does every winter is like it's a reset mechanism on the lake. And as the new spring comes, the lake has started from a common point. Air bubbles have come up. The gases that are dissolved in the water will lodge in the ice. Well, in the wintertime, it becomes an asset for everybody.
The lakes are definitely one of the best assets the city has. Skating, ice fishing.
They can walk, they can ski, use ice boats, they can go fishing. Get outside and enjoy it. On a day when it's really bitter cold, you get a crack that shoots across the ice, and the ice spreads. And then on the next really warm day, the ice will push up. The lake thunder is caused by the ice expanding and contracting. A ridge of broken ice jutted out on the lake.
The lakes for Land's End are certainly an asset for our employees, but another constituency that it's really important for us is our recruitment efforts. We're constantly trying to attract the best and brightest from a talent standpoint. Those prospects coming into town and enjoying downtown, enjoying the lake.
There was recently a review of the lifetime of past civilizations on Earth, and the mean duration was 336 years. And so we're kind of coming to the end of our shelf life here if we don't do something about it. And it's going to be the young people at this meeting who are crucial to saving global civilization from itself and getting out there with a positive message that we can do it better. There are these examples all over the world of people managing water resources in creative, sustainable ways, and we can get that message out so people have hope and can move in a positive direction. I thought back to Henry David Thoreau, an American activist and pioneer, actually, of peaceful civil disobedience in America, and his cause was abolition of slavery. And he inspired later great Americans like Martin Luther King and others. And Thoreau was really frustrated by slow progress of society to abolish slavery, and he sought solace in nature. And he went off on a long canoe trip on the Concord and Merrimack rivers, and in the trip he reflected on the slowness of social change, and after he got back he wrote a beautiful essay about the trip, including a moving reflection. And I'm really encouraged by all the conversations here about outreach and education, and so clearly there's interest, people are learning how to do it. And I think we all just need to get busy and do it. I think old scientists like me play a role in breaking trail and creating cover for the young scientists so they can do these things, and I certainly intend to do that as long as I can.